Today we're talking about NPM malware and Electron applications because they're closely related. So I guess I'll just repeat what I was saying. So NPM malware is super pervasive because NPM is a super commonly used package application manager for JavaScript applications. And some quick stats here. So 500 plus NPM packages were hit by the Shalai Halud worm, which I think it's probably more by now. I know tens of thousands of GitHub repositories were affected. And that's a worm that basically, if we go back to Security Plus vocab, it is a self-replicating virus that spreads to other computers automatically. And it's basically steals NPM tokens, GitHub tokens, whatever, and tries to spread to other repos or NPM packages. Axios is a major NPM package used for web request stuff, and it's super popular, and it was hit probably a month ago with it was compromised. Its main maintainer was compromised, and they pushed a what was said to be a remote access Trojan to it. I think it was caught pretty quickly, but still definitely affected lots of people. These other two are just other major NPM packages that have been affected by supply chain attacks. I realize I'm on the wrong slide. Okay. So today, though, we're going to talk about the main triggers. So what actually gets these NPM, what actually makes these malicious additions go boom? What makes them fire off? So on a technical perspective. So these are three main ones. They're not all encompassing though. So we've got pre-post install scripts, which is basically an addition you can make to the package.json file, and you can basically run arbitrary commands in the when they run npm install, which is something they're always going to do when they pull down a new repository that uses npm. And the next one is backdoored pull request. So basically, someone raises a pull request with some realistic looking addition that also has a malicious functionality hidden somewhere. So this is pretty common as well. You could either do it from an external GitHub user, or you could compromise, somebody who's a maintainer or is able to push pull requests. And then the last one to talk about is basically an account, a GitHub account or something like that, that gets compromised through either GitHub personal access token or some other phishing method, and they push malicious code that way to repositories that the user has access to. Okay, so let's jump into this first one. So the npm install, pre-install, post-install script. So basically, it allows the person who maintains the code repository or whatever to add custom install commands. In this case, I have bad and batter, which in this case, I don't think it would actually run the way it's written, but you can thank Claude for that. Basically, you would add something like, you could add a bash command here. You could add a node command to run some other arbitrary JavaScript file. You could even run Python. It's really up to the bad actor in this case, but it's a simple way when they run npm install to get something to fire off. So I'm actually going to show this one real quick. We'll jump over to this Kali machine. So we have a simple code repository here where we've got an index.js and a package.json. This package.json, we've just defined a pre-install and a post-install command. You don't need both, but just demo purposes. So we're just going to run node malicious.js, which if you had made additions to the package or whatever, you would just add, they would just add that file and then add this line here that can execute it. And all this demo file is going to do is basically grab the current environment variables and print them to a file called stolen.txt. So in the real world, you might send this out with a web request. You might look for GitHub tokens, anything in environment variable wise that could be in like a CI/CD pipeline or something like that, or just on the developer machine. You could also add persistence mechanisms and whatnot. So all that is needed to trigger this is like they would pull this down with git clone or whatever, and then npm install. And at this point, it's already been done. So you can see this in the command line. So that could cause a flag, but in a lot of cases, it's easily, you can easily make it believable. And then in this stolen.txt, we have all the environment variables that were present at the time. I even wrote a little fake token here. So that's one of the ways you can trigger this code execution through JavaScript backdooring packages. So pretty easy, pretty straightforward one. It's a legitimate like feature used by JavaScript code repositories. So it's hard to be like, oh, that's malicious. It's going to come down to things later down the road to detect. So we'll jump back here. All right. So for backdoor pull requests, pretty straightforward. This one can be more of a social engineering tactic. So basically, if you're an external GitHub user, you might create a GitHub account that, it looks like somebody who's a contributor or something like that, and raise a pull request with some juicy looking feature you've added, enough to get them to pull it down and try to run it themselves or see if it's, works. Or there's also the possibility of an insecure CI/CD pipeline they might have that, like a GitHub workflow that runs on any pull request, even from non-maintainers. And then you could have code execution in a GitHub workflow environment. So access to like secrets or something like that. There's also the possibility of if it's a compromised user who's a maintainer, but they're only able to, raise pull requests. They could raise it that way. And then you're mainly still targeting developers though. And it's going to be, some sort of hidden backdoored file, or, added dependency. I think with Axios, they added a dependency that was like some plain crypto thing or whatever. And it pulled in. So instead of having like the pre-install, post-install thing, it would just add a dependency, one line, name of a package, and then it would pull that NPM package, which can execute as it's pulled. So yeah, this one's pretty straightforward. And the last one I want to talk about is phishing a contributor. So this is pretty common with a very popular NPM repository. So basically, developer for Axios, I think, was specifically targeted because he's the maintainer of such a popular repo that's used so widely. So I think it was like a pretty involved social engineering like tactic that was used, and then they compromised his NPM token, and then were able to push directly to NPM some malicious versions of Axios. But it could also be, landing on the developer's workstation and getting access tokens and then pushing to GitHub or it could really be a lot of different ways they would do it. But phishing a contributor directly is for sure popular method. Okay, cool. So let's move on to the Electron apps. So I want to talk about Electron apps because they're so closely related to the NPM malware ecosystem, because Electron apps basically are just Java Node.js apps. They're basically just web applications that have two different components. So there's the renderer that is basically like its own browser that is used to render a GUI app for the user. And this makes development a lot easier for people that want to develop desktop apps, because they don't have to work in something like Qt, which is like C++ or C#, depending on what operating system they are developing the app for. They can just use Electron, and it's basically web app development, and then they just package it as an Electron app. It does use a lot more memory, but you know, who cares? I'm not really a developer, so I don't focus on that kind of stuff. But for our discussion today, Node.js is what's used in the background so that the desktop app can actually interact with the operating system it's running on. So a lot of the apps you probably use are Electron apps. Notion, Asana, Slack, Teams, VS Code, Cursor, like these are all Electron. Fortinet client, these are all Electron apps. And I think they're getting more and more popular as time goes on, because they realize, oh, it's normal to just have like 64 gigs of RAM. So like, it doesn't matter if my Electron app uses 3 gigs of RAM. So anyways, there's a big component to Electron apps, which is called the ASR file. So the ASR file is basically a bundled up zip file of the application. The Electron runtime will load this ASR app or this ASR file into memory, and then this is how it executes the app. So there's going to be inside of the zip file, the ASR file, there's going to be a resource, or inside the resources file, there's going to be this app.asr. It's going to contain all the JavaScript, HTML, images, stuff like that. So when you see an app like myapp.exe, it's not like the myapp.exe is not a binary compiled version of the app in the way that like a C++ app is a compiled version of the app. The actual app is inside of the resources app.asr file. So this is interesting because Node.js is obviously a server-side language, so it can execute things server-side. We're talking about like cross-site scripting and stuff like that. It's not usually a super critical server-side impact because it's not executing on the underlying OS, whereas Node.js is. So when you talk about this ASR file, there's different ways we can modify the JavaScript that's inside of it and execute code on the host. And that's why Electron apps are being used, and that's what we're going to talk about. So they can really be used in a couple ways, but mainly persistence and initial access. So you can modify an existing Electron application and backdoor it with some JavaScript, even just add JavaScript to a file that already exists and execute something on the host in that way. So that would be like an initial, and redistribute it. That would be an initial access like way to use it. Persistence would be, say you have code execution on a host, say one of the methods we were talking about earlier, and then you look for every Electron app on the host and try to insert JavaScript into accessible files in the Electron app. That would be a persistence method, which I covered in, I think, episode 3 of this series, where Plone CMS was hit with a NPM malware that basically looked for all the Electron apps on your computer and tried to replicate itself into them to maintain persistence. So it's definitely used in that way. But we're going to talk about, or I'm going to demo kind of what these Electron application files look like, and how easy it really is to add code, backdoor code, to these very legitimate applications and kind of go undetected, because you're not doing things that are overtly, let's say, historically flagged on. So you're not doing low level memory manipulation because you're existing in Node.js, which is a managed runtime. You're not doing shellcode injection, you could try to do that, but in the example I'm going to show, would just exist in Node. So let me move over to Windows, actually. My VM turned off. So the first one I'm going to kind of look through the packages on is Slack. Slack is a Electron application, but there's some interesting nuances about its file system and how we can essentially just change a file, add some code to a JavaScript file, and execute code. Let me show it in this Kali VM first. So I've got it here. So I've just got this file. It's just a proof of concept. It's basically like message box. When you're talking about Windows, it's just going to display a message box. So in real life, this would be whatever the malicious NPM package is doing, or implant, or whatever. It could spawn subprocesses. It could do whatever it wants, because it's Node.js. It's has full operating system access. It could, as the user context, it could read files. It can do whatever. So, but in this case, I'm just going to use this little snippet as the example. Let me log in. Let me adjust this. It looks weird. Okay. So one of the biggest indicators when you're looking at these Electron applications is it written in the app data local file, or is it in under program files? If it's under program files, you're not going to be able to write to it as a non-admin user. So it's a little less useful, I guess. Although you could still maybe use it for initial access, because you could just take the application files and have them run it from their downloads folder or something like that. That might be, there's different levels where you could detect certain behavior, like running something out of the downloads folder. But in this case, Slack's actually in the app data local directory. So even if you had code execution on this host from some other method, you could just write into different Electron files. So if we go into the actual app, we see a bunch of supporting DLLs. Most of these are .NET assembly DLLs. Some of them are native binaries, but if we look at them, all of them are going to be signed by either Microsoft or whatever distributor creates it and maintains it. So digital signature is really important for code integrity and making sure I don't, replace one of these DLLs with one of my own and then do some sort of DLL side loading. So that used to be a major thing, was like look in the folder for an unsigned DLL and then replace it with one of your own. That's like a beacon or or whatever it is. DLL sideloading's pretty well detected nowadays, depending on the EDR you're talking about. But the behavior itself, loading an unsigned DLL into the process, is detectable. Let alone like if there's a big size difference between the original DLL and that DLL, then. So when we talk about the JavaScript landscape, inside this resources folder, we're going to see app.asr and actually an unpacked version of app.asr, which Slack is one of the only apps I've found that does this, where it actually unpacks it and keeps it unpacked and loads it from the unpacked folder every time, instead of usually it's unpacking it in memory every time, so that, if someone wanted to tamper with this, they would have to unzip this and replace it with a backdoored version. But in this case, the files are actually already just unzipped, and meaning you could just write to them instead of tampering, unzipping the ASR file. So basically, when I'm going through this, I'm looking for different node modules that are definitely going to be loaded into the runtime as soon as the app is loaded. And you basically can just go through and add. Some of these don't even have JavaScript files. They have these .node files, which are essentially DLLs with a specific export function that allows you to load the DLL into node runtime and execute like native functionality. But some of them definitely do have JavaScript, like this one here. And so you can look at the JavaScript and it's JavaScript. But what we can try and do here is, first I'll just show, we'll go back, we'll launch Slack. It usually launches out of here. I deleted the LNK file, but launches, looks normal. Although it is slow because it's, it takes a lot of memory. Let's see. And then you're going to see all these child processes. So it takes, 100 something megabytes for one, though. Let me see in total. Okay, 665 megabytes of memory. You're going to see these child processes, which are like those renderers, or they're the worker nodes I was talking about. And then the main one, I believe, is the renderer, which is the kind of browser-esque part of the application. So, okay. So it loads. The other good thing about Slack as a, from a threat actor perspective, is it runs in the background. A lot of apps run in the tray. So like they're going to be running in the background. So anyways, we're going to kill that. And now we'll just go into that JavaScript file I was talking about and show that if we just write to it, so I'll just go down to the bottom and I'll write this this other file that I had ready. I'll just write the contents here and minimize this. And if we relaunch it, we should see that our little dialog pops up. Slack continues running in the background because it's loaded this asynchronously, so it's not going to like halt the main process here. And this code execution that we had can run and do anything. So it could be running in the background the whole time, giving us, like callbacks, or it could just be running some credential stealer or whatever. So it's a super valuable region or like application infrastructure to attack for an attacker, because we didn't have to do anything. We didn't have to do like shellcode execution, which is super detectable nowadays. We didn't have to write memory to anything. We just add some JavaScript code. So especially nowadays with AI, you could rapidly prototype a implant in JavaScript and have that added to Slack, and then zip this all up and deliver it to somebody. Another app I've been looking at is Asana. So Asana is also a Electron application, and it's going to look very similar. So you'll see this app 271 is just your current version. And you're going to see the supporting DLLs, and then you're going to see this resources. But unlike Slack, it doesn't have it unpacked already. So in this case, you actually need to, if you want to modify stuff, you actually have to copy it. I don't know if it'll let me copy to my other VM. Let me see. I could probably just do it in this folder. So I'll just copy it, rename it to a .zip. And then extract it. Oh, you know what? It's actually won't let me do it that way because you need to use the ASR unpack tool. So let's see, what's our IP? So if I spin up a web server, I should be able to just transfer it that way. Or I'll use updog. Pip install updog. Let me do this. Oh. All right, let me just make a virtual environment. So I just use updog because I can do uploads instead of just downloads. So bind to all and port 8080. So let me see. These VMs should be on the same network. So, all right. So I'll just do this file. And I'm just uploading it to that directory. So it's actually pretty big, so 110 megabytes because it's the whole application. So anyways, we have this file, and I think it's ASR unpack or something. Let's see. Extract app to extracted. Yeah. So if I open up this folder, we should see the app files. So now we can see the app files of Asana, as in Electron app. And so I would just go through different JavaScript files and see what you'd basically have to edit them and then repack it at the ASR file and replace it to see which ones execute or if they do execute at all. There are code integrity mitigations that Electron developers can put in place so that it basically checks the file hash of the ASR file. But it seems, at least at this point, a lot of them don't do that. I don't know if there's a specific reason, but let's see. one that's like not that big. Preload. And then this obviously uses a ton of node modules. I'm just going to add it maybe to a couple. Let's see. This one's all obfuscated. Make sure we don't break JavaScript. Do it there. Do it there. And then what you would do is, let's move this to a backup file and then ASR pack extracted. Cool. So it'll show up as, oh, I thought it would show up as a zip, but it does show up as Electron ASR. And then what you would do, I got to restart that. Is download it, delete this, and copy it over. Now, I haven't tested this, so I actually don't know if this would work, but let's see. Oh, it looks like one worked. Yeah, so it looked like one of them fired. So yeah, like, and then you could just repackage this like into a zip file or whatever. And for red team engagements, that's how you could deliver it. For attacker perspective, that's, you know, backdooring common apps and then getting Google advertisement is, you know, like pretty popular attack vector. I don't know if Asana is just really slow or if it's because of what we added. But in any case, I've used this method to deliver like C2 beacons because if you don't have to deal with, if you don't have to do the things that are getting traditionally detected, like process injection or shellcode injection, manipulating memory allocations in stuff like C, and you know, I like that stuff, but it's just gets detected nowadays because EDRs, it's been used so much. EDRs are just finely tuned for that kind of behavior. Whereas they're not finely tuned for this behavior, especially because what constitutes malicious JavaScript versus non-malicious JavaScript that's executed in a Node.js runtime within a process is going to be way harder to detect than stuff that's running as native, like assembly code. So that's kind of the main reason I think we see the shift towards interpreted languages like JavaScript, Python, you know, OSA script or whatever on Mac. And I think it's probably going to continue that way until there's either better detections or better mitigating controls. In this case, Electron can add mitigating controls to their apps, but it's up to the individual Electron developers to actually enforce it. For instance, I know on Mac OS, it's a lot harder to modify these Electron apps and backdoor them because of integrity checks. So it's really going to come down to the individual developers. It's going to be treated just like DLL sideloading was, which was down to the developers, because it's not a real vulnerability. It's just like a bad practice that's being taken advantage of. But for the time being, threat actors are going to take advantage of it. So that's pretty much all I had planned for today. Let's see. Yep. That's pretty much all I had planned for today. So thank you for joining. It was a good time, and I'll see you on the next one. Bye.